Hey, what's up everyone? Welcome to Descriptive / Laboratory Chemistry Part 8. Today we're going to be talking about crystal field theory. Crystal field theory is a way to describe the bonding in complex metal ions that we can't do with a lot of our other models. Crystal field theory also helps describe some of the characteristics of these complex metal ions that, again, we can't describe with the other models that we have. So crystal field theory talks about complex metal ions. What is a complex metal ion? A complex metal ion is just a compound with a metal ion at the center, and it's surrounded by a number of other molecules or ions. Those molecules or ions that surround the metal ions, we call them ligands. So if I give you an example, if you look at this complex metal ion here, you can see a copper at the center. That's going to be the metal ion at the center, and it's surrounded by these 4 ammonia molecules. Those ammonia molecules are the ligands, and so the entire thing with a charge of +2 is going to be a complex metal ion. Now, complex metal ions are a bit different from the bonding within the complex metal ion is a bit different from normal compounds. The bonds between the metal ion and the ligands are known as coordinate covalent bonds. So, in a normal covalent bond, you have a 1-to-1 sharing of electrons. In a coordinate covalent bond, one species is going to share both its electrons with the other one. A good analogy is like, imagine you're at school and you're having lunch with a friend, and you guys both of you have different snacks, so you decide, I'm going to share my snack with my friend, and my friend is going to share my snack with me. That's a normal covalent bond. You guys each share one. Let's say one day you forget your snacks, and your friend has 2 snacks, so they decide to share both of them with you. That would be a coordinate covalent bond. In the case of complex metal ions, the ligands are the ones that give up the 2 electrons. So my friend would be the ligand and I would be the central metal ion. All of those ligands are going to now function as Lewis bases, because when you're sharing both your electrons, that's analogous to being a lone pair donator. And a lone pair donator is the definition of a Lewis base. So all ligands are going to function as Lewis bases. Alright, that's a background of complex metal ions. Let's talk about crystal field theory. So crystal field theory assumes an ionic characteristic of the metal-ligand bond. So in the center you have your metal ion with a positive charge, and around it you have your ligands, which have a negative charge. The fact that we're assuming an ionic characteristics means that we're assuming point charges. So in the center you have a positive charge, and around it you have these negative charges. So the ligands are attracted to that central ion because they are point charges. Negative attracts a positive. And you can see a diagram of this. So you have a central ion at the center and you have 6 ligands around it. Okay, let's look specifically into the electrons of the central metal ion. So in the central metal ion, you're going to have some sort of metal. And if you look at the d orbital of that metal, its orbitals look something like this. You have 5 degenerate d orbitals, and 2 of them are going to be on the same axes as the ligands. So if you draw the ligands on this diagram, the ligands would be like here, 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 here. They'd be on those poles. What happens now is that those ligands are negatively charged, and the electrons in those d orbitals are also negatively charged. So you face repulsion. But not all repulsion is equal. If you look at the repulsion from this d orbital, I think the last one would be like here. If you look at that one, the repulsion is going to be less, and that's because the negative charges of the ligands are further away from the electrons. But if you look at this diagram here, if you look at this orbital, the electrons are right next to the ligands, meaning you face more repulsion. It's the same for if you look at this one. This one, the ligands would be here, and those electron clouds are further away from the ligands, so you face less repulsion. There's one more orbital which faces a lot of repulsion, and it's the one over here. And again, it's because those electron clouds are on the poles of those ligands. So as it turns out, when we assume an ionic characteristic, it means that these 2 orbitals are going to face more repulsion, electron-electron repulsion, because those d orbitals are on the same poles as the ligands. What that means is that your 5 degenerate d orbitals are no longer degenerate. You're going to have different levels of energy based on how much repulsion you face. If you look at another diagram for it, you can see the metal ion at the center, and then it's surrounded by these ligands. If you look at like these ones, those electrons are really close to those electron clouds, so you face repulsion, but these are a bit further away. The ones over here are further away, so you face less repulsion. Again, all this leads to a splitting of the d orbital. So the d orbital starts off like this. You have 5 degenerate d orbitals, which means that they all have the same energy. And what happens is that they get split up. The ones that face the most repulsion get elevated into a higher energy level, and the ones that face less repulsion get, lowered to a lower energy level, I guess. And specifically, it's the z2 and the dx squared minus y squared orbitals that get elevated to a higher energy level. And that's kind of a mouthful, so we decide to add some terminology. We call those two orbitals that get moved to a higher energy level, we call those the Eg orbitals, and the ones that get lowered, we call those the T2G orbitals. And the difference between the Eg orbitals and the T2G orbitals are signified by delta naught. Delta naught represents the octahedral crystal field splitting energy. We'll talk a bit more about what that octahedral bit means, but the crystal field splitting energy is the difference in the energy between the higher energy level, the higher d orbitals, and the lower d orbitals. And in octahedral ones, and again we'll talk more about what octahedral means a bit later, but in octahedral ones, Eg goes up 3/5 of delta naught, and T2G goes down -2/5 of delta naught. So if I made up some imaginary numbers, let's say this was 100, I don't know what units, Eg would be at 160, and T2G would be at 60. Alright, so recap, the orbitals that face the most repulsion get elevated to a higher energy level, and the ones that face the least repulsion get lower to a lower energy level. And the difference in their energy is signified by delta naught. But delta naught isn't always constant between all complex metal ions. You can have a different delta naught based on certain things. So what determines the magnitude of delta naught? Well, it's going to depend on the ligand that surrounds the complex metal, the metal ion at the center. And the series of ligands and their, magnitudes of delta naught are represented by the spectrochemical series. So at the left you have, this is an experimentally determined series. So at the left you have the ligands that produce small delta naught values, and the ones at the right have large delta naught values. So cyanide would have a really large delta naught value, and iodine would have a small delta naught value. The ligands with small delta naught values are called weak field ligands, and the ones with higher ones are called strong field ligands. So again, cyanide would be a strong field ligand, and iodine would be a weak field ligand. Alright, let's look at how electrons are going to fill up these split d orbitals. So if we were dealing with just normal d orbitals, 5 degenerate d orbitals, they would fill up according to Hund's rule. So if we had those 5 degenerate d orbitals, they would fill up something like this. So the first 5 would go in one at a time. The orbitals are going to fill up one at a time before they start pairing up. And afterwards, they start doubling up. The reason they don't like to double up initially is because, remember, these orbitals are spaces. These are wave probabilities. So if both electrons are filling up the same space, then you're having more electron repulsion. When you have more electron repulsion, you have a higher energy system. And these systems always want to minimize their energy. But of course, we don't have 5 degenerate d orbitals. We have 3 that are degenerate, and then 2 more that are separately degenerate. And it's going to be different based on if you're dealing with a low delta naught or if you're dealing with a high delta naught. So let's look at low delta naughts first. For low delta naughts, you're going to fill up the bottom 3 first. So you're going to have 1, 2, 3. And then you have to decide, is the next electron going to go to the higher energy level, or is it going to start doubling up? And in the case for low delta naught values, they're going to go to the higher energy level. The reason for this is because it takes more, there's more energy involved in the electrons doubling up than the electrons getting promoted to the higher energy orbitals. So for low delta naught values, you have the electrons going up to the higher level, higher energy d orbitals. After you have 5, they're going to start doubling up from the bottom. So you have one more here, one more here, one more here, and it just fills up, goes to the top layer, and it fills up. And that's all of your 10d electrons. It's a little different for high delta knot values though. So for high delta knot values, you obviously start off at the bottom and you get your 3 done. But then you have to ask yourself again, does the next electron go up to the higher energy levels, or does it start doubling up at the bottom? In the case for high delta knot values, it takes less energy for them to double up than to get promoted. So they start doubling up. And once they double up, after they're done doubling up, they then go on to the next energy level. They go one at a time, and then they double up. This whole principle of all these electrons wanting to go single and then doubling up is what we call Hund's rule. Hund's rule. Alright, so that's how electrons are going to fill up these orbitals, and this will come up more when we talk about the magnetism. For now, let's talk about what we were talking about when we said octahedral. So in the examples that we used a metal ion and it's surrounded by 6 ligands. When you're surrounded with 6 ligands, you have a specific splitting of the d orbital known as an octahedral splitting. But octahedral splittings aren't the only ones. If you had different number of ligands and they were oriented different ways, you could have a lot of different other splittings. For example, square planar and tetrahedral both come from having 4 ligands. And the difference in them is based on what ligand you have and what their orientation is. But the takeaway is that octahedral isn't the only type of splitting in crystal field theory. You have a bunch of others: pentagonal bipyramidal, square, anti-prismatic, trigonal bipyramidal. So there's a lot of different ways to split it, but we use octahedral for demonstration purposes because a lot of the times you are going to be dealing with 6 ligands. And octahedral is relatively simple compared to a lot of the other ones. Like if you look at square planar, you have 4 splittings compared to 2 which you have in octahedral. So the reason we use octahedral is for simplicity and for demonstration purposes, but no, it's not the only splitting that's possible. Okay, so let's start talking about what properties can be explained using crystal field theory. The first one that we're going to go over is going to be the color of solutions. So certain transition metal ion aqueous solutions are going to be colored. Like if you have a compound with copper 2+, it's going to be this light bluish color. So why does this happen? Well, imagine this electron and it's around the nucleus in these shells. Electrons don't orbit around shells. They are in orbitals. These are they exist in probabilities. But for the sake of explaining why some of these solutions are colored, it's helpful to just say that it's that they exist in shells. So let's say you're zooming in on one electron here in the first electron shell, and it's in its ground state. What happens is that let's just decide to introduce some light to it. Let's introduce white light. White light is light containing all other wavelengths of light. Light is a form of energy. It's a form of electromagnetic radiation. And so what happens is that the electron can absorb some of that energy and get excited. It moves up to a higher energy level. And in this case, it went from 1 to the 4th energy state. But this electron can't always stay in this excited state. It's got to come back down. And when it comes back down, let's say it started from 4 and it came back down to 2. Where did that extra energy go? Well, the electron is going to emit it in the form of electromagnetic radiation. And depending on if that electromagnetic radiation has the right wavelength, you could produce visible light. The jump that we went from the level 4 to level 2 is part of the Balmer series. So if an electron jumps from the 4th level to the 2nd level, it's going to produce this green light. If you were to jump from the 3rd level down to the 2nd, it's red light. Blue to 2, that's blue. 5 to 2, that's blue, and then 6 to 2 is purple. There's other series. You can have other different types of jumps. If you went from 6 to 1, that'd be in a different series. But the reason we don't care as much about those series is because they produce UV light or infrared light instead of visible light, so we can't see it with our eyes. Okay, so recap: electron takes in energy, it gets excited, it has to come back down, so it emits that extra energy in the form of electromagnetic radiation, and if it's the right wavelength, it's colored. How does this play into crystal field theory? Well, I said that these electrons don't really live in shells, but they do live in these two sets of degenerate d orbitals. So instead of having shells, let's look at them in the form of these orbitals. I realized I forgot to put one of the shells here, but there should be an extra orbital here. But let's say we do the same thing to this system. We add white light. White light is light containing all other wavelengths of light. And let's say there's a wavelength that's the perfect amount of energy to excite this electron to the higher energy level. So now it's in its excited state. It's analogous to the electron moving up to a higher energy shell. But same as the other diagram, it's got to come back down. And when it comes back down, it's going to emit that extra light, extra energy in the form of electromagnetic radiation. And if it's the right wavelength, then it could be visible light. So the whole thing with crystal field theory is that instead of having those separate energy levels, those shells of different energies, you now have two different sets of degenerate d orbitals, or more sets of degenerate d orbitals, depending on what kind of splitting you have. But the electron can move around on those. And when it gets excited and it comes back down, it can emit that energy in the form of electromagnetic radiation. There's a special relationship between the wavelength of light that the electron absorbs and the wavelength that it emits. So if you see that the color of a solution is blue, it means that the wavelength of light that it absorbed was this yellow light. If you look at a color wheel, the color of the solution, if you look opposite of it, it's going to be the color that was absorbed. So if we say that the electron emitted some green light, then that means it had to have absorbed the red light over here. You just look opposite of a color wheel. There's also a special relationship between the wavelength that you absorb and your delta naught value. So if you absorb a long wavelength, then that means your delta naught is small. Remember, electromagnetic radiation is just a way for energy to be transported. A longer wavelength means that you're transporting less energy. If it takes less energy to excite the electron, then that means that the difference between your two sets of d orbitals is smaller. So long wavelength equals small delta naught. If your wavelength was short, then that means you're carrying more energy. If you're carrying more energy, then that means it took more energy for the electron to move up to the higher energy orbital. So your delta naught is large. And that's how colors work in the perspective of crystal field theory. Let's talk about magnetism, because crystal field theory also plays a part in magnetism. So in magnetism, you're going to have two different types of magnetism. You're going to have paramagnetism, which represents an attraction towards a magnetic field, and you're going to have diamagnetism, which is a repulsion, albeit weak, from a magnetic field. So a compound could be paramagnetic or it could be diamagnetic. If it's paramagnetic, it's attracted to a magnetic field. If it's diamagnetic, it's going to have a weak repulsion from a magnetic field. How does magnetism play into electrons? Well, if you look at paramagnetism is going to be associated with more unpaired electrons. If an electron is unpaired, then it's more likely, if a compound has more unpaired electrons, it's more likely to be paramagnetic. And this is because their magnetic moments add up. So these electrons have spins. And we say that when it's, facing up, we have a spin of 1/2. And you have a bunch of 1/2 spins, and all these spins are just going to add up. And then you have a magnetic moment of 2.5. So in paramagnetism, you have a lot of unpaired electrons, and all of those help build up the magnetic moment of that compound. In diamagnetism, you have more paired up electrons. When you have more paired up electrons, that means you have a spin of 1/2, but you have a spin of -1/2 right next to it. So what happens is that these end up getting canceled. Their magnetic moments cancel out. So you're left with a magnetic moment of 0. So your magnetic moments cancel, and that's why diamagnetism means you don't have an attraction towards a magnetic field. So how is this going to play into crystal field theory? Well, it's going to have a lot to do with small delta naught values and high delta naught values. If you look at an example, let's say I have a compound with 6 electrons in its d orbital. Let's see how these electrons would get paired up if your delta naught value was small, and how they would be paired up if your delta naught value was large. In a low delta naught value, they would get paired up one at a time initially, so 1, 1, 1, and then they'd move up, so 1, 1, and then the last one would just be doubled up. In this case, you have a lot of unpaired electrons. You have 1, 2, 3, 4, and they're all 1/2. Since all these spins are going to add up, you're going to have a high magnetic moment. It's going to be more likely to be paramagnetic. You have more of these unpaired electrons. But let's look at what happens when you have a high delta naught value. In a high delta naught value, you're going to have 1, 2, 3. But unlike low delta naught values, it's not going to move up to the higher energy level d orbitals. It's going to instead pair up. So when you start pairing up these 6 electrons, what you notice is that all their spins are going to cancel out, and you're going to be left with a magnetic moment of 0. What that means is that the one on the left is a high spin complex, and the one on the right, is a low spin complex. The more your spins add up, the more likely it's going to be paramagnetic, and if all your spins cancel out, it's going to be diamagnetic. And that's how crystal field theory affects how a compound behaves around a magnetic field. It's going to be based on your delta naught values, the difference between your splits in d orbitals. And that's magnetism. So let's review crystal field theory really quickly. Crystal field theory is a model for complex ions that assumes an ionic characteristic of the metal ligand bond. So you have a metal ion at the center surrounded by these ligands, and since you are assuming an ionic characteristic, the electron clouds of that metal ion are going to interfere with the ligands, and you're going to have repulsion. But the repulsion is not going to be even. Certain ones are going to face more repulsion than others. And what that means is that your degenerate orbitals are no longer going to be degenerate. They're going to split up. The ones that get elevated to a higher level are called the Eg orbitals, and the ones that get elevated are called the T2G orbitals. This particular splitting is an octahedral splitting, and that happens when you have 6 ligands, but you have a lot of other different splittings that can occur. Crystal field theory helps you explain magnetic properties and also colors. And that's about it for crystal field theory. Alright, that's all I have. I hope you were able to learn something, and I hope to see you later. Thank you for watching.